And then now we're going to actually, Dr. Kasser gave us a recording, so I'm going to actually present the recording, and then Dr. Kasser will take questions afterwards.
Hello, I'm Joseph Kasser, and what I'm talking about today in my second annual Chesapeake chapter talk is building a better systems engineering postgraduate course, the research, the pedagogy, and the results. And some of them surprised me and will probably surprise you. Topics I'm going to cover are purpose of the research, the multidisciplinary research, what to present for learning, not necessarily teaching, and some of the subsystems, conceptual and otherwise, and how to present it. That's the pedagogy. The prototypes and the feedback from students and other people, what I call the 4% solution, the lessons learned, and then let's see if you can be a part of that 4% and where that 4% came from. The purpose of the research. Traditionally, one would write to create a course to expedite the creation of outstanding systems engineers, some of whom will become technical leaders, or as we called them in Singapore, engineering leaders. So we need to determine, 1, what to teach outstanding systems engineers, 2, the best way to teach it, and 3, how to fast-track teaching that comes from experience. If it's going to take you 30 years to become an outstanding systems engineer, well, by the time you've done that, your industrial career is about over. Construct the course and prototype it. You think that's a good way? Wrong. You've got to look at it from a different perspective. The systems approach is create a system, not a course, a system. Instead of determining what needs to be taught, we first need to determine what systems engineers need to know. Because before we know what they need to know, we don't know if we're teaching the right thing. And then instead of determining the best way to teach it, we've got to figure out the best way to learn it. And then how to fast-track learning that comes from experience. And then construct the system and prototype it. So we're now into multidisciplinary research. We've got to understand systems engineering, what they need to know. We've got to go into the educational field and learn about learning and do some research into that. We've got to work out how do you fast-track experience into learning. Moving on, the multidisciplinary research. Well, magic happened. The outcomes from the research were a journey spanning 3 continents and 20 plus years. I came up with a set of requirements for creating outstanding systems engineers. And I had to develop new and innovative systems thinking and systems engineering tools because some of the information I had could not be understood without creating a framework or some other tool to use. Lots of publications nobody seems to read. On my website and some are on Incose, and there's some YouTube videos that nobody watches. This will end up being one of them. And a number of upset and uncomfortable systems engineers in Incose who felt challenged and confronted by some of the questions I was asking. And they were being taken right out of their comfort zone and didn't like it, and still don't like it. And it's a paradigm shift, because in order to be an outstanding systems engineer, you are totally away from the process paradigm. And I came up with a prototype. It's not a course, it's a program, and the course is only part of it. It began in December 2020 and it's still running, and I'm now mentoring a few potentially outstanding systems engineers. And even though I have to get up at 5:30 in the morning in my winter time, I find it's worth it. Moving on, let's go into what to present for learning and some of the subsystem concepts. Part of the research showed that there are 5 types of systems engineers. The apprentice who has to be told how to do something. Type 2, the practitioner who has the ability to follow a process. Type 3 is the problem solver who has the expertise to conceptualize the solution but cannot define the problem. Type 4 has the ability to examine the situation, can define the problem but cannot conceptualize a solution. And the type 5 who is both a problem formulator and a problem solver, and when this person becomes the engineer leader, projects really hum. And the colors refer to problems and solutions, cans and cannots. After developing the 5 types from observation, did a literature check, and I found this table. The problem solvers and the problem formulators differentiated between the abilities to find similarities and differences. And I can map those into the types. The innovators or doers are just type 2, problem solvers are type 3, problem formulators are type 4, and the innovators are type 5. And when I group the types, I find that systems engineers are type 1s and 2s, good systems engineers are type 3s and 4s. And look at the differences. A system engineer creates the system. They're given the set of requirements and they can go ahead and create the system. A good systems engineer creates the system the customer asks for or solves the problem the customer poses. That's the type 3s and 4s. But the type 5, or the outstanding systems engineer, creates the system the customer needs and solves the real problem. Notice the difference. Well, looking around, based on observations of systems engineers and students over about 30 years, I came up with something like this. Systems engineers are the green, good systems engineers are the yellow, and outstanding systems engineers are in blue. And the numbers are based on the Pareto principle or the 80-20 rule. And we discussed this in the Oasis Cafe one session, and people agreed with the numbers. I found that interesting. And let's take a look at one way in which people can grow. Systems engineers become good systems engineers and eventually become outstanding systems engineers. Well, what does it take? To be a systems engineer, that's basic training in applied systems engineering. What's that? Get to it in a moment. It's one of the tools that I had to develop. So your CSET knowledge, for example, helps you become a systems engineer. Good systems engineers have advanced training in applied systems engineering, some project management, some training in pure systems engineering. What's that? Get to that in a moment. They have experience and they may have the book learning degrees and so on. But in order to become an outstanding systems engineer, that really takes a mind shift. In order to bridge that gap between good systems engineers and outstanding systems engineers, you need advanced training in pure systems engineering and project management and a lot more experience, and you definitely need to be mentored. How do we determine what they need to know? The traditional way to do it is observe the scenarios of what systems engineering are doing in the workplace. If you do that, you don't know what's missing. You don't know what they should be doing but are not doing. This can institutionalize poor practice, and it's the business process re-engineering as is model. You then articulate the requirements, and then as far as the process is concerned, you identify factors that makes learning effective, and then you come up with scenarios and requirements as above, and then you combine the product and the process into the system that will create outstanding systems engineers. That's bad, because it can institutionalize poor practice. So what's the better way of doing it? The product is outstanding systems engineers, so you conceptualize scenarios of what systems engineers should be doing in the workplace. That's the difference. This is the BPR 2B model. You then articulate those requirements and the process, identify the factors that make learning effective, scenarios and requirements as above, and you combine into the system that will create outstanding systems engineers. So the difference is you determine what the systems engineers should be doing as opposed to what they are doing. Now, when you're trying to understand a situation, there's the old story of the blind men feeling the elephant. The elephant is the system, and they're trying to understand the system from a single perspective, and they're not making it. So we need to understand the system from several different perspectives. One of the tools that I developed years ago, 20 years ago now, was I was trying to develop that body of knowledge based on what systems engineers are doing and what they should be doing in the workplace. And based on their role, they were doing an awful lot of stuff. We put together this framework that has Derek Hitchins' 5 layers of systems engineering or complexity as the vertical layer and the states in the system lifecycle as the horizontal layer. And then we could see the scenarios in developing requirements, capturing requirements, or doing integration, doing testing, and so on. But we found that they were doing so many different things that the body of knowledge would have to encompass project management, systems engineering, all the specialities, and a whole lot of other stuff as well. So we gave up on it at that time. But the key concept that allowed us to get over that came a lot later, when we split systems engineering up into systems engineering the role, which is what the systems engineer actually does in the workplace, architecting, engineering, and so on, and systems engineering the activity, which are the traditional activities associated with systems engineering. I'll give you some examples in the next slide. And the observations are, as I just mentioned, each person's role is a different mix of activities and maybe from more than one process domain. And a type 5 person in one role may be a type 3 person in another role due to a lack of something. And so SETA is conceptual design, requirements elucidation, management, architecting, interface management, testing, and so on, modeling, and others. And I looked back through the literature and I found one example that's probably well known, Sarah Sheard's 12 Systems Engineering Roles, published in 1996. But I also found, in 1969, 12 earlier roles published by William Jenkins in the systems approach. And these are totally different. I like role 5. By his overall approach, he ties together the various specializations needed for model building. There are 3 types of SETA. Pure systems engineering, that's what I call systems thinking and beyond, the cognitive skills of systems thinking, problem formulation, quantitative methods, decision making, and so on. And then there's the applied systems engineering, which I mentioned earlier, SETA, the traditional activities. Then there's domain systems engineering in the problem, implementation, and solution domains. There are 3 different domains, and each domain may be totally different. For example, if the problem is traffic congestion, the solution may be a subway, and the implementation domain may be tunnel boring, or may include tunnel boring. 3 totally different domains which require specialized domain knowledge when dealing with the problems. That's where multidisciplinary teams shine. It's similar to mathematics, which is split into pure and applied math. But if you look around at what's being taught currently, most of what's being taught is applied systems engineering, although my data is dated. We can relate pure and applied domain SETA as follows. Systems engineers using cognitive skills while performing activities in a role in 3 domains. The cognitive skills is pure systems engineering. The activities in the role are applied systems engineering. The 3 domains are the domain systems engineering, problem, solution, and implementation domains. So what was my initial approach? Well, what is the first thing outstanding systems engineers do, or usually do, when they understand the nature of the problem? Plagiarize. What? Actually, it's determine what other people in the past have done when faced with the same or similar problem. It's the concept behind TRIZ, and then you examine and adjust the other people's situations and your situations for similarities and differences in the situations. You modify what they did accordingly. You don't just copy what they did into your situation. It may not be appropriate. And so coming from academia, my approach was to reuse course components to create the system. I knew I was going to have a course as part of the system because that's the basic way these days we do the education. So the education sum system would be a course. How do you create that? Well, I went back and looked at what are the processes for crafting a degree. There's the benchmarking approach, which is benchmark other universities, aggregate the topics, position yourself on top of the normal distribution curve, and teach most common topics. Didn't like that. because you're benchmarking other universities, but who says they're actually teaching what systems engineers need to know? What I thought they were doing was they were bundling the most common modules with modules that faculty can teach. Don't like that either. So invented one, and it was published 2005. You take the customer needs, the body of knowledge, and the benchmarks. That's the other university part. Customer needs are both the students and the student employers. You create the subject matter, knowledge and skills, and then you figure out the delivery mechanism and factors that make learning effective. So not only do you have your systems engineering domain, you have your educational domain. That creates the pedagogy, you deliver the classes, and then you have the feedback. You assess the teaching and learning results. It's a continuous loop. And so my classes tend to be different each time they run. Hopefully they're improved. Usually when I was working at NUS, I would look around each year and benchmark other universities. But in 2013, I took the opportunity to do a serious benchmarking study based on the institutions that were exhibiting at the Incose Symposium in Philadelphia. I think it was Philadelphia. 10 different universities, and I was benchmarking our Master of Defense Technology System degree. And so if I looked at what was teaching based on that HKMF, I found that all of them were pretty much teaching down at the system level, which was to be expected. The courses they were teaching were requirements, design architecting, and integration and testing. And this is based on required courses. You can read the papers and see the detailed information if you really want to. And then Eileen Arnold and I looked at whether they were teaching pure systems engineering, applied systems engineering, domain, and so on. And we found nobody was teaching domain systems engineering except number 8 had a little bit of it. They all had courses in management, and you could actually get a degree from Institution 9 without doing a single required course in systems engineering. So a lot of the focus was on applied systems engineering, as I meant earlier, although there were a little bit of pure systems engineering. Now I had to think about what is systems thinking, because outstanding systems engineers need systems thinking. And it really depended on who you ask or who you read. It's difficult to learn, it's difficult to teach. There were 2 schools of thought, systemic and systematic. We looked around at it and came up with a holistic approach to use both. So we used the problem-solving process, be all the blind man. Look at the different versions of systems thinking, and there were about as many different versions of systems thinking as there are of systems engineering. I was able to group all those definitions into 2, systemic and systematic. So when we aggregated the views, we found that systems thinking is thinking about the system as a whole to gain an understanding of the system. The most useful view I found was Barry Richmond's 7 streams of systems thinking. And systematic thinking is applying a methodical, step-by-step manner or process to think about something or to achieve a goal. That's the problem-solving process. And then we go beyond systems thinking because, as this person, whose name I cannot pronounce, said or wrote in 1999, we need both systemic and systematic thinking. There are some people for whom systemic thinking is system thinking and that's it. There are other people for whom systematic thinking is systems thinking and that's it. And the people describing their systemic thinking were having different descriptions as well. And then more than that, I found that Ackoff wasn't entirely correct. Not sure I want to argue with Russ Ackoff, but Russ Ackoff was working in operations research, and he was treating systems as black boxes, whereas sometimes we need to look inside the system and see what's going on. So if your car won't start in the morning, understanding how the car is used, how it relates to the traffic, the roads, and other adjacent systems won't help you determine that the battery's flat. Sorry, Russ. And so the perspectives you need to understand the situation depend on the problem. And you need even more perspectives to solve the problem. So we developed the holistic thinking perspectives. There's the elephant. We're looking at the situation. Big picture, operational, functional, structural, generic, continuum, and temporal, quantitative, and they all come together with a person, and the scientific perspective is the outcome of the thinking, the hypothesis, the guess, or whatever you want to call it. And in this instance, the elephant was systems engineering. We needed critical thinking. I looked at different ways of measuring critical thinking, and I found Susan K. Walcott's 5 levels. I liked them and has used them. No reason to reinvent a way of measuring critical thinking. So we put them together into a proposed maturity model back in 2010. And this is modifiable for different situations. So the knowledge of systems engineering, applied systems engineering, is related to the different types. The domain systems engineering is related to the different types. Pure systems engineering is related to different types, and then the individual traits necessary for the job are also listed. So if somebody needs communication skills, management skills, leadership skills, negotiation skills, whatever they are, you could put them in for that particular job. You could fill in the different domains in which they're working. If they're working in aerospace, they would require one set of knowledge. If they're working in industry, they would need different sets of knowledge, and so on. It's easy to tailor for different organizations in different domains in different stages of the life cycle. So we took a look at what's being taught against Competency Model Maturity Framework, and we found out, sure enough, they're all teaching, except for 8 and 9, applied systems engineering, and a few of them are teaching bits of pure systems engineering. As far as the cognitive characteristics are concerned, yeah, not much, but not too much. And the individual traits, not too much. 2 years ago, Professor Howard Eisner published this book on what makes systems engineers successful. It provides a description of how and why systems engineers can be and have been successful. He did a great IV&V job, independent verification and validation, on the set of requirements I came up with separately. Thank you, Howard. He offers the successful attributes, focuses on the key positive values, drills down into the success features to aim for and the failure characteristics to avoid, and he sets a model for achievement and behavior for future systems engineers to follow a successful path. If you're in any way interested in improving your systems engineering, this book is a must. It's thin, it's small, it's easily readable, and it's got a lot of good stuff in it. We've figured out what systems engineers need to know and only explained a little bit of it. And now we have to deal with how to present it. From an operational perspective, a desirable situation in academia is you have a lecture by the instructor. It summarizes the knowledge for the session and the reading, highlights the main points, adds additional material pertinent to the lesson. At that time I was doing the research, people were talking about using the flipped classroom. Instead of the lecturer giving the lessons, students read the material and they come to class ready to discuss it. Great idea in theory, but it doesn't work in practice. Then you have group exercises, and that short discussion facilitated by the instructor is based on an assumption that isn't valid. So the instructor is lecturing instead of discussing. There has to be a better way. And then you look at it from the functional perspective. Students have different learning styles. Some learn by seeing, some learn by hearing, some learn by doing. That all has to be taken care of in optimizing and expediting the learning process. Something that's not really done very well in traditional academic settings. And teachers have different teaching styles. Some like lecturing, some like discussing, some focus on the type of knowledge, etc. And so you end up with boredom, poor performance, and dropout. I can't tell you how many classes I have been bored to death in by the instructor. People are bored, they don't listen, so they don't do well on the exams. Nobody explains to them the importance of doing well on the exams. And then you get dropouts. And when you're dealing with tertiary education and there's competition for places in the classroom, dropouts are really a waste, because not only does the student drop out, but because they got in, they prevented somebody else from getting in who might not have dropped out. We need to do something about that. And then there's issues with the effectiveness of the delivery method. I found this data a long time ago based on Dale's cone of learning and the learning pyramid, and I redrew it in this way. You can see that lecturing and reading are the actual worst ways of learning something. And so what I did in my course was I turned that around. Instead of requiring the students to read the material before coming to class and discussing it, I require my students to read the material and then make a presentation based on the material. Top way of learning something. Practice by doing. That's the exercises, as well as the discussions. So the traditional flipped classroom doesn't deal with the top two. It just goes from lecture to discussion group. And then you've got to deal with attention span. I found this, published in 1953 in technical classes. You can see how attention span goes up in the first 5 minutes, and then it goes down slowly, ends up as a minimum at around 30 minutes, and then it starts peaking up at about 40 minutes. Book did not say how long the classes lasted, but I expected it was about 40 to 45 minutes. Because the attention span was picking up when the students were waiting for those magic words, class dismissed. So what's a more desirable situation? Based on some of the requirements I found, providing the 5 top aspects of the engineering design process, very similar to the systems engineering process, that best equips secondary students to understand, manage, and solve technological problems. Multiple solutions to a problem or requirement. Oral communications. Graphical or pictorial communications, ability to handle open-ended, ill-defined problems. What are those? Wow. And systems thinking. Also, what we need to do is grade based on the cognitive skills and knowledge and incorporate the higher levels of Bloom's taxonomy. Remember that we need to go beyond systems thinking because systems thinking provides understanding, but holistic thinking identifies the problems and provides the solutions. So I went back to the benchmarking data to see if any of this was being taught, and guess what? None of those 5 aspects showed up in any of the wording in any of the course descriptions on the websites of those 10 institutions, except a slight allusion to systems thinking in 3. Prototyping and feedback. Early prototyping results. I published this back in 1999. And I published this one in 2000. These were based on the similarities between classes and symposium results because I was looking into improving the effectiveness of distance learning. I came up with recorded lectures, and so I was the first person to record lectures in the distance learning class at University of Maryland University College. If you think about it, there's not much difference between a classroom session and a conference presentation. You make the presentation, you discuss it, and then you move on. I ran the class twice. Students came up with 2 different versions of the technology. And so when I hear about the problems Incose is having with the hybrid, I just laugh. Those problems were solved 20 years ago. I told you I published a lot of stuff that nobody read. And if you're concerned about grading, those academics amongst you, look at the difference between face-to-face grading in the same class. Not much difference, really. And then I had a hybrid class. This was the capstone class in which one of the projects was to develop the online web conference. By 2000, I had moved from Maryland to Australia. The class had several teams. I forget whether it was 3 or 4 teams met in the classroom in Maryland. And one team was purely online because we had online students there. And there wasn't much difference between the quality of what was produced by each of the students. And remember, the instructor wasn't even in the classroom. He checked into the classroom using distance technology. Problems of using that was solved way back, which helped me for the research. So I ended up with online lectures, knowledge reading, not so much the flipped classroom. There could be classroom sessions, and that all sort of ended up talking about blended learning. A set of exercises that were designed for authentic assessment and workplace emulation, which is a different goal to designing specific exercises in the classroom. And so when I looked at how those components in the subsystems related to Wicklein's requirements, lectures don't tell you very much. Exercises, well, they're experiencing them, and in the knowledge readings, they're experiencing some of them as well. So there isn't actually one component that will solve all the requirements. It's the system together that does that. And if I looked at Bloom's taxonomy in terms of evaluating the cognitive skills, lecturing has no evaluation of the cognitive skills because there's no feedback. Exercises, Well, when you're doing an exercise based on the knowledge that you've acquired, yes, you can pretty much do levels 1, 2, and 3. 4, 5, and 6 are a little more difficult, but 4, 5, and 6 came in very nicely in the knowledge readings. And that also gets over the flipped classroom approach. Grading was based on this. The benefit of it is students can pass the course with basic cognitive skills, so you don't fail type 2 students. They just get low grades. So when I put all those requirements together, I find that lecturing is not a very good way of demonstrating compliance to requirements. It's open loop. Exercises, yeah, but it's difficult. Knowledge readings I found were the best way to show the knowledge, and they also went well beyond systems thinking, and the ability to handle open-ended, ill-defined problems depended on the external readings and the exercises. Ability to handle open-ended, ill-defined problems, those are type 3 and type 4 skills. And the cognitive skills, knowledge reading tested 5 out of 6. And, well, the individual assignment depended on the type of exercise or the type of assignment. And when they only present a single solution to a requirement, you can't tell whether they have seen multiple solutions. And individual exercise is definitely not teamwork. Here's an example of an exercise in risk management. Notice how I've highlighted the cognitive parts of it. Conceptualize at least 2 risks, at least one way of mitigating each identifying risk, and then produce a presentation, thinking about the problem and reformulating it, thinking about the lessons learned. There's the skill of cutting down everything to a less than 5-minute presentation. And then the knowledge readings, here's an example of a knowledge reading exercise, and the cognitive skills highlighted in yellow. Formulate the problem, summarize the contents of the reading, show the compliance matrix, show this slide and the version number of the lesson. That's when I look back later, a year later or so, I can see what they were actually exercising. List the main points, that comes from the summary. Reflect and comment, compare content, and bringing external knowledge. State why you think the reading was assigned to the module, and summarize the lessons learned, and so on. High cognitive content. Comments from students. When I taught this in class in Singapore and Brunei, I've learned to look at problems using systems thinking perspectives and generate ideas based on different perspectives. Learned systems thinking, critical thinking, holistic thinking. The course teaches me on how to think holistically and manage ideals using the tools. Applying techniques, applying systems thinking to real problems. Systematic concepts for identifying the problems. More importantly, I have learnt new perspectives to look at a system. The results in the grades, well, the initial grades match the student's behavior. They can be adjusted to curve by moving the changing threshold. Here's one class with one set of grades, not adjusted on a curve, and here's another class with a different set of grades, not adjusted on the curve, but you can see that the first one, where there's a minimum at B+, shows split cognitive skills. Students are more in the A's or the lower B or the B's, and the comments from students tend to reflect the cognitive skills. Students with high cognitive skills loved the classes and complained it was a lot of work, but they learned an awful lot. Students with low cognitive skills didn't like that extra work. What did I actually produce out of this? Well, the 4% solution is a program with no time limit, 52 weeks, synchronous live weekly Zoom groups, and they're recorded. New participants absorb material from the people who've been in the class longer, and they may not understand everything right away, but they soak it up in the way we traditionally learn things. The exercise emulate the real world, and so there are knowledge reading presentations as well. I can correct immediately any misinterpretations of the material that session. It doesn't have to wait till the exam at the end of the class. And participants can discuss real-world problems, so out-of-box experience in other domains, and we do that. And learning by absorption fast-tracks the learning and the experience. You're getting the experience in another domain, and you're learning to think about how you can apply what happened in that other domain to your situation. And there are also one-on-one sessions available. They can be booked anytime. There are asynchronous short lectures that introduce the topics, and there are asynchronous discussions in the private LinkedIn group. We started in Facebook few of the participants had Facebook accounts. I found that a lot of systems engineers don't have Facebook accounts, so we moved it over to LinkedIn. The asynchronous discussions are very useful in that they allow people time to think before responding, because there's no requirement to answer a question or make a comment right away. It's similar to posting stuff in LinkedIn and Facebook anyhow. We can put in notices of interest. Somebody will point out that there's something going on somewhere and they will copy it into the class group. Also add references to additional material of interest and resources and so on. And it's self-paced for individuals. There's no requirement to make a presentation each class. There's no requirement to complete the work each class. But beware procrastination and use just in time. The instructor becomes your coach and your mentor, and that's at least $50,000 value if you work that out on an hourly basis at what highly qualified people charge. And it's a good opportunity to extend your personal network by meeting like-minded people facing similar problems in systems engineering and what to do about it when they see things differently to their colleagues. Course architecture. The lectures are self-paced, so you can stop them, you can replay part of them. This design was responsive to a few participant comments that the lecture was too fast, especially when I'm dealing with students for whom English is a second language. This way they can play the lecture back until they understand it. The exercise allows you to participate applying what you've learned. You post your responses to the exercises in the asynchronous group, and a good source of material to use as comparison in the knowledge reading exercises can be found at ResearchGate and Google Scholar, as well as textbooks in your company or the university library. The interaction takes place in two ways: a live Zoom meeting and questions and comments in the asynchronous group within a specified time limit. When I started prototyping this, I offered participation free in December 2020 and January 21 to my past online students who showed potential type 5 characteristics, and Incose and the general public via LinkedIn. So what happened? There were 10 initial expressions of interest, 4 initial shows in the Zoom weekly sessions. None of the people who showed were in Incose as far as I know. 4 more joined during 2021 and 2022. 3 dropped out. 1 is sort of active in the alternate live session. He has shown up in the Monday live session and actually made 1 presentation remotely. He recorded the presentation and we played that in class and commented on it. He viewed the comments the following week when he looked at that recorded session. 1 student graduated, that is, he went through all the modules and did all the exercises, and still drops in occasionally to take part in the discussions. The lessons learned, it's postgraduate. This is not postgraduate, and it's not for everybody. Free doesn't work. There's no need to complete an exercise before presenting it. Actually, it's preferable not to, and I'll explain all these in a moment. Students show progress quickly. Students need time to adjust to this class. Is there too much content? Probably. It can be a lot of fun as well as being educational, and further research is needed to find the optimal class size. I mean, any good research project ends up with the need for further research. Let's go through them. It's not postgraduate, it's post-postgraduate, because it doesn't fit into the semester or the traditional cohort type of class. You don't all start at the same time and go through it at the same rate. People are going through it at different rates. They're in different states. So some of the people are in module 2, 3, other people are in modules 4, one person's in module 7, and so on. It all hangs together quite well. So it's a hybrid of the master apprentice and the classroom educational models. It's more than book learning, and most of the value is in the program architecture. You can read all the materials, they're all available. The value is in the interaction and the discussions of the material as well as the material, and in the way it's done, which you don't get in the traditional postgraduate or continuing education workshop or class. Most traditional academics without real-world experience could not lead this class format, because you're making judgments all the time. You're using those higher cognitive skill levels all the time in this class. Participants can join any time. They learn by immersion and iteration. That's key as well. And there's a lot of shared real-world experience in different domains, and there's no firm ending date. It's a resource. Participants can come back to it any time. It's not for everybody. Every session is different. I never know what's going to be discussed in a session because people do different exercises, people come with different problems, they tell different stories. And sometimes nobody has done an exercise, so we discuss a problem somebody's having or start applying some of those cognitive skills to a real-world situation that's going on at the present time, like COVID or Ukraine. So lesson plans are pretty useless. You can get a quick idea by looking in the LinkedIn group ahead of before the class session, but then not every student publishes in LinkedIn before making the online presentation. Sometimes the publication in LinkedIn comes later. So you need to be knowledgeable and experienced to guide the participants in reaching solutions. So we're creating knowledge in the class rather than telling as a traditional instruction. It's a master-apprentice role. Students and participants, there's a high application, rejection, and initial dropout rate. People come to me, they want to be in the class, and I talk to them for a while, and I say no. Somehow I don't push them or pull them into the class because I don't think they can handle it. And even those they did come in, there was a high dropout. Participants need the right aptitude and experience. Without that, they won't stay. And they need to be internally motivated to learn and succeed. My classes are definitely not for minimum level of effort students. My classes that I teach or taught in the university and this program. I offered it for free. Free doesn't work. Motivation varies according to the circumstances. In the early days in Facebook, there were some lurkers in the Facebook group. Facebook tells me who's accessed the material. I could see names there that never showed up in the weekly Zoom session. Finance is a motivator. It's a tangible incentive. I now charge enough dollars to make it serious. There is a list price, but there are generous discounts to Incose. Nobody's taken me up on that so far. If somebody is really motivated and I see that they really want to be in and I think they can do it, there are ways to pay that make it doesn't hurt so much, but it's got to hurt enough to make sure that the person is motivated to stay. Otherwise, I've wasted my time and they've wasted their time. The exercises are designed to emulate the real world of iteration. Some outstanding systems engineers prioritize and work iteratively until the schedule is resources. They don't try and understand every point in a linear sequence. They skim and go round and round until it's done. They know that how much time they have and they balance the time. That way they don't get hung up on one point and spend all the time on that one point. NASA used a similar technique in the Apollo program where every activity on the moon had a time limit. If it wasn't completed at the end of the time limit, stop, move on to the next one, come back if you've got time. Same technique that you're supposed to use on answering multiple choice questions. Generic thinking, similarity. If you think about live classroom exercises, they're only the first iteration because you only have 20 minutes to do the exercises. So some students can take 4 or 5 or 6 hours to do the exercise, and I keep telling them, no, don't. Just take an hour, get it down. Because when you're spending a lot of time to complete the exercise, you're really reinventing the wheel. They need to learn to present a work in progress, even when the way forward is clear, because they get comments and we discuss where should we go from here. We create knowledge. The student has a much better understanding of what's going on there because we show the mistakes along the way. And I actually use this process in the Oasis Cafe to develop this presentation, or at least parts of it. It emulates peer reviews, informal, teamwork, and so on. The real world is not the academic world. These exercises emulate much of the real world. Students show progress quickly. Feedback is provided on content, correctness of content, presentation graphics, and layout. Exercises emphasize iteration and repetition. So the requirement, as I mentioned in the example exercise, reformulate the problem according to the problem formulation template is a required part of every exercise. So they get practice using the tools and practice using the thinking. And sometimes we think about alternative ways of presenting the information. Should we use a bar chart or a radar plot to present the information? And why one way is better than the other way? And so sometimes ask the student, show that information in a different way, come back next session, and we'll discuss the comparisons. Don't see that in traditional class. And students can compare their presentations made in later sessions with those in the earlier sessions. So somebody can look back to something they did 2 or 3 months ago and they go, wow, I'm so much better. Students need time to adjust to this class. They're mired in the academic paradigm with respect to exercises. This is a different paradigm containing some different real-world emulation. It teaches a different paradigm. It's that gap, that chasm between good systems engineers and outstanding systems engineers. They need to learn the iterative approach to the exercises. And what's more, the exercises are optional. You don't have to do an exercise at all. But if you don't do them, it reduces the effectiveness of the learning. If somebody has a lot of work or family issues or something like that, they don't need to come to class and make excuses for not doing the exercise. The exercises are done when the person is able to do them. Although I will nudge people if they don't do exercises for a few weeks. So work, family, and other commitments don't affect the learning. Mistakes that students make in the exercises are learning opportunities and provide discussion points. The best presentations are those that provide lots of learning opportunities. In the traditional classroom and in the real world, the best presentation are those that contain no mistakes. In the classroom, the best presentations are those that provide lots of learning opportunities. Does that mean they contain lots of mistakes? A learning opportunity is based on something that was done wrong, or a way to improve something that was done, meets the requirement, but it could be done in a better way. The readings are not meant to be read from start to finish. They should be scanned iteratively, gaining more understanding in each iteration. And that's mentioned at the front of each book. Too much content? Probably. I started with the traditional 10 modules at the beginning, and a module may have several parts. Each part of a module may have more than one exercise. Modules contain an introductory lecture and in-depth readings, and the website is designed for impact. When you go in there and look at the website, that's probably why those people didn't show. Pure systems engineering changed from 2 modules into a separate prerequisite program. 2 modules were not enough. I found that people were missing the concepts, or either I wasn't explaining them too well in 2 modules, or they didn't pick it up. So I turned them into a different program called Creating Outstanding Problem Solvers. And it's a prerequisite program to creating outstanding systems engineers. Flexible content. If I need another module in depth on a SETA activity, one can be developed to order and becomes a resource. So I could, for example, put in an in-depth module on requirements, or a module on bringing systems engineering into an organization. Lots of people seem to be facing that, but they don't realize it's an organization change problem. Implementation domain is organization change. Let's see if you can be part of that 4%. Remember this? The 4%? How do you bridge the gap? Can you cross that gap? Do you have what it takes? Are you stuck in the type 2 process paradigm and want to get out of it? Are you interested in crossing that gap? Or are you interested in finding out if you can? Join me in a small group for at least 30 days for free. Full access to the 2 programs. Just go to my website and you can find the button that will take you to the class. Ask not if you can afford to do it. Ask rather if you can afford not to do it. In summary, I covered all this material. If you have any questions or comments, if you're interested and don't want to try the program at this time, talk to me and the others in the online Oasis Cafe using Zoom. I'm also online at other times. I really like to thank Bruce Lerner, Raed Al-Kazi, and Shirley Tseng, who made useful comments in the online Oasis Cafe during the preparation of this presentation. See, I use some of the techniques that I teach. Thank you very much for attending. For those of you who are in the session in the Chesapeake chapter meeting, I'll take questions and comments now.
Okay, can everybody hear me?
Yeah, I hear you.
Oh,
Yes.
good. All right. So awesome presentation. A lot of material there. A lot of stuff went by. So if folks have questions, feel free to unmute yourself or put something in the chat. I see Pafford had a comment. Good postgraduate systemic approach looks well suited for SE certificates. Anyone have any comments or questions?
Hey, Jeff, it's Dave Fadley. Last number of years, I've done a lot of, my job role is kind of more of a consulting where I spend a number of 6 months, 12 months on a new problem to be solved with new groups of people and all that kind of stuff. And interesting enough, one comment I have is what I found I ended up doing as a lifelong learner is to do a lot of, not in a classroom type or setting, but to do a lot of the things you were kind of talking about. In other words, trying to learn the domain in which you're in, quickly create some things that are in a very simple tools that are, quickly pulled together to help solve a problem or define a problem, whatever is needed, and start putting iterations and stuff out there. Some of the challenges are a lot of people aren't used to doing that, and they just do their own little independent thing on the side and don't know how to handle that kind of stuff either. But it is, I find, useful in a come in and in a new environment, new people to do that kind of stuff. You have any thoughts on that?
Yes, I think so. It depends on what type you are, if you're a type 3 or a type 4. I find that type 2s, when they're faced with open-ended problems, can't handle them and just talk about complexity. They don't recognize the difference between a well-structured and an ill-structured problem. Systems engineering is all about dealing with well-structured problems. You have a set of requirements, and that gives you a well-structured problem for the system you're going to create. But in the earlier state, back in the early state where you're trying to define the problem, you're dealing with an ill-structured situation. It's an ill-defined problem, and type 2s cannot handle it. You need to be type 3 or type 4.
Yeah, and you said like 80% plus are in the, not type 5 or whatever it is. And that,
So
of course,
80% of your systems engineers are type 2s.
Right. And I'd say your non-system engineers that probably get 99%. I think that way, which is usually who you're working with or who you have to try to influence as well. So that's another challenge.
If you're dealing with somebody who has good problem solving skills, somebody talks to them about process, they just laugh. Because they're way above that. They create the process. They use bits of the process to create a custom process which creates the solution. That's the step-by-step methodology for creating the solution. It's not taking a systems engineering process and applying it. It's solving the problem.
Hey, Joe, one thing I noticed too, you talked about at first you offered it for free, and there was probably greater people sign up for it, but actual participation was not there. I just anecdotally, I find the exact same thing when we attempt to offer tutorials or stuff through the chapter, is when they're free, I'll get a ton of people sign up for it, and then the day of the tutorial you get like a handful. But it's sort of the opposite. I don't know whether it's like a combination of like people don't value it if you don't put a price there. Like, well, actually that's exactly what you were sort of implying or saying. But when I put a price tag on it, even if it's something nominal, you tend to get people who sign up committed. And I also think it indicates to people that like, oh, this has value, you know, so, you know, it's not just, you know,
What it's
something
like
that I should like to be doing.
you go into the shopping center and you see, oh, you see something given away for free, so you take it. And later on, you may, when you get home, you find you've got absolutely no use for it, so you throw it away. So it's free. Yep, I'll sign up for it. But when the time comes, oh, I'd rather do something else, so I won't bother. And so I used to spend time on the phone or on Zoom talking to people about the course and deciding that they didn't have the skills, or they were more type 2 people than anything else, and they wouldn't benefit by the course. And I decided I'm going to stop doing that because it's a waste of time. If you're interested, go take a look at the material. It's all there. It's up to you.
Yeah. Hey, one other question I had. Yeah. You had said like, you know, the class isn't for everybody, both student and instructors. I was just wondering, and obviously, you know, because you were saying, you know, the people have to put the effort into it. The students need to be mature enough that they need to be self-motivated to work at it. But I was wondering also for the instructors, do you think the typical instructors would find this so different that it, you know, they would also find it more work for them, and so, you know, a little bit less attractive from an instructor's point of view?
Well, there are instructors that know their stuff because they've done it, and they have both the academic qualification and the experience. And then there are instructors that teach the book. And an instructor that teaches the book can't handle this course because we're dealing with real world examples. When I was doing my doctorate and I was taking courses at GW, I got a B on a class in systems engineering because when I took the exam, I saw gray where the instructor saw black and white. And so I gave the real world exam answers rather than the book answer.
Oh, right.
So when a student poses a problem, you've got to have the instructor has to have the experience or the ability to think about the problem and help talk the student through the problem to understand the situation and guide the students towards creating the answer themselves. And I use this technique in industry. I'd go into a meeting where people are facing a problem and I would tell me about it. And there was sometimes I would say, let me ask you a stupid question. Why are you doing that? And sometimes they would think about it and say, oh, we're doing that because we've always done it. Well, why? And then in some instances, they find out they don't need to do it anymore. And when they stop doing it, all the undesirable aspects of the situation have gone away. So it's the ability to think and ask questions is just as important as the domain knowledge. And you can pick up some domain knowledge very quickly. And by asking the questions, who, what, where, when, why, and how, from different perspectives, you end up learning more and helping them, the clients, learn more about what they're doing. And people used to say, how do you know so much about our domain? Or that's what the question meant. It wasn't quite in those words. And I would just smile because I wasn't going to admit I didn't know anything about the domain other than what I read on their website and a little bit of looking and a little bit of Google searching or the equivalent before the meeting.
Interesting.
So how many Most of the people in this session must be type 2s.
Possibly.
Hey, Joe, I got another question for you. So a lot of organizations, at least I've seen, have a proclaimed, mentor-mentee kind of programs. My experience has been they're nowhere close to that master apprentice type thing where you're basically spending a lot of time and energy teaching and doing and spending, a huge amount of time doing it. But if they would take that one step further, I could see that doing it because you have real engineers who have the training and have a lot of things in there who could do that kind of stuff. Have you gotten feedback from companies who try to maybe think about and implement that kind of thing and take that one step further to do the master apprentice type? It takes a huge commitment to do that.
Not much, but I do know, and I've done it myself, it takes time. And some people are not willing to take the time. Also, I've been in one experience where the apprentice wanted me to do the work for him. Like tell him exactly what to do in every instance. And that's not a good way of teaching somebody, because if you tell them what to do each time, then you're doing the learning, not them. I had a discussion once with somebody at the University of South Australia. He was guiding a doctoral student through the research, and he was telling the student exactly what to do, step by step by step. And I didn't comment at the time, but afterwards I asked him who was getting the degree, him or the student. Because a good mentor will talk to the student and help the student think through the situation and come to the realization by themselves. Or if they don't have sufficient knowledge, he or she would point them in the direction of getting that knowledge, because getting the knowledge is better learning than being given the knowledge.
No, I mean, I agree with that. My experience, most profit-making organizations won't pay people to do that. For some reason, they haven't gotten to a point where they'll pay people to teach and mentor most of their time doing it.
They do, but they don't get the best out of it. Because if your mentor comes in and is just a teacher, not the most effective way. On the other hand, it does get the job done, which is what the organization is interested in. Organization wants to get the job done in the quickest time, which is a slightly different goal than improving the employee.
Yeah, they kind of conflicting goals there in order to.
But there are times when you use one, and there are because of the need. So I'm not saying it's bad in every instance. There are times when you have to get a job done. The water level on the dam is sort of coming up to the top, and you have to sort of fix the dam before it breaks. Well, in that case, you don't have time to go out and research dams and whatever. You have to be told, do this, do this, do this, do this. And that's the way in that particular situation.
Right. The other way they brought up recently was, we try, but nobody does it to the extent they should, which is kind of a post-mortem lessons learned if you've been through a task or a project, and really take an in-depth look at that stuff and learn from it. And most people I've seen will do a very cursory view of that if they do it at all.
There was lessons learned came into vogue maybe 20 years ago. And then they started being a requirement to document the lessons learned at the end of the project. But there was no requirement to actually read those lessons learned. I call them write-only memories. Because we don't teach that. Somewhere in those slides, I said, what's the first thing an outstanding systems engineer does when they understand the problem? We don't teach that. We don't teach that when you're faced with a problem, find out what somebody else did, because 99% of the problems that you're faced with, somebody else has already experienced it. I mean, unless you're going to the moon or Mars, which, well, going to the moon now has happened, so we know what they did. But unless you're going to Mars or a manned mission to Mars, that's an out of this world problem, literally. Nobody's faced it before. But probably everything else, it's been faced before. Go see what they did. Don't reinvent the wheel. Make new mistakes. Don't make old mistakes.
Hey, I see Greg Olson has his hand up and he put a comment. Did you want to state your?
Yes, I've heard some really good things here from both these gentlemen previously, but his comment about lessons learned, I'll use an aviation example. We could do the goods, bads, and others after each flight, monthly, and periodically, like the end of a cruise or anything else like that, because, you know, very, very blunt, what was good, what was bad, and what are the others? What could we have done differently? What would we have done differently if we had different resources, if we had different perspective, everything else, and capturing that. And both Bruce and our speaker here have both Joseph have given me a lot of advice in the past at the cafes and everything else, and they do a very good job of helping analyze that and helping assess that. Now shut up.
Okay. For folks, we're definitely going to provide the YouTube link to this, as well as our comms team is going to do an after-action report. You'll be able to get to it from our website, which will obviously link to the YouTube video.
How long would you like me to delay before I make the link public?
I think like just a couple days. I can check. I think less than a week, maybe.
Okay,
like
because
3 or 4 days.
You should put it on the Chesapeake chapter site first, so
Yeah.
that people go there.
Yeah, we would like that. Is it possible for us to download the video? Paul can put like sort of a splash, Incose Chesapeake splash page at the beginning or something.
If you've got the right software,
He does.
You can download YouTube videos. Yeah.
Okay. Okay. All right. So we'll do that, and I'll check with those guys to see how quickly they can get it up. Usually, it's. I don't want to commit them to anything, but usually it's less than a week. So
okay. So I'll go into YouTube later, and I'll say August the 1st as a release it.
Okay.
That should give you enough time.
Thank you. I think there's one other question we'll get.
I mean, before you do that, did you take a picture of all of us, Clinton?
You know who did that was Dave during the member.
I already have it done.
Oh, okay. All right, good.
Thanks, Kaz. Yeah.
Kind of a reminder there. Okay.
Bruce Lerner has a question.
Okay, Bruce. Yeah, go ahead.
Yeah. Hi, Joe. Just one thing I was thinking about as you were presenting was, do you have any feel for the timeline for this course? How long would you expect this to take with a moderate work environment, home life situation? Is this a 1-year course, a 2-year activity?
How long is a piece of string?
Okay, well, you surely have some experience with at least the student that you suggested.
Okay, one student went through it pretty quickly, but he went through the systems thinking when it was 2 modules.
Okay. Mm-hmm.
And the other students are going through systems thinking or the cognitive skill course when it's, and they're going through it pretty slowly, mostly because they don't do the exercises because something comes up and they've got a work schedule issue or they've got a family issue, and so they don't do the exercises. But you stay in the course as long as you want. So at the beginning, the exercise rate is pretty good. they do an exercise every session. And then the enthusiasm falls away. The interest is there, they come, but they may not do an exercise every session. And in the beginning, people were trying to complete trying to complete the exercise. And that's what was taking them long between sessions. When I kept, after some reminders that they don't have to do the whole exercise, they can present a work in progress, the rate began to pick up. So they do bits of the exercise and we talk about the bits of the exercise, and then, so they're moving through the exercises, but parts of it in a session.
Okay, interesting. Thank you.
Okay. Awesome. Let me share this real quick to finish it out. Just want to give you our formal appreciation, thanks, gratitude for being able to host you. Especially, we're really appreciative. You know, this was sort of premier information that Dr. Kasser was presenting. This is the first time he's presented the results in whole, I think, for this. So we're really appreciative of that at the Chesapeake chapter.
Okay, may I remind people, join the Oasis Cafe.
And can you tell them how to do that?
Bruce, you want to tell them how to do that? You're running it?
Let me see. Yeah, so if you go to the Fur Cafe site on LinkedIn, or I'm pretty sure it's primarily on LinkedIn, there should be a link there, and it takes place on Thursday evenings, U.S. Eastern Standard Time at 7 o'clock. So there is a link. If you would like, I'll go grab it and drop it in the chat. I hadn't thought that was coming, but we can do that.
Yeah, that would be useful. And then we'll include that in the after action report. So when people go to see that, they maybe also have access to that.
There's also a link on one of the later slides, last slides, there's a link to it too, for the people who watch the YouTube.
Okay, cool.
Yeah, the slides will, Clayton has the slides, so he can pass them out. I'll post them.
All right, so I'm going to do the raffle real quick here and we'll wrap things up. I'm going to spin the wheel of fortune. See who tonight's winner is. Get that via your registration email. And I want to thank everyone. If anybody has anything else they want to ask, feel free. Otherwise, you're dismissed. Or hang around and chat with some friends if you want. Either or. Joe's going to bed, right? Or no, it's your morning, right?
It's my morning. It's 9:45 in the morning.
Oh,
There was
okay.
a question there. Mark Kaz had a hand up. It went down again.
Mark Kaz, did you have a hand up?
No, that was just me giving the thumbs up to the winner of the book.
Oh, sorry.
Okay.
But I think I have a copy of the book, so I'm not jealous.
Oh,
I don't think I've read it yet, but I've certainly have bought, I think, 3 or 4 of Dr. Kasser's work. So
Thank you. If you check into the class, you can download a PDF version of the book. So anybody who didn't win the prize.
oh, okay.
So, hey, Joe, has it been pockets of system engineering thinking who really have taken this kind of approach to heart in terms of the master apprentice and have seen some good results as well? Or is it still so new that are people still just kind of standing back?
I think people are standing back, and Incose sort of really doesn't like it. Gets me into a lot of trouble when I talk about it.
I'd like to talk to you about it offline sometime, but we missed you at the Oak Cafe this morning.
Yeah, I mean, it sounds like, I mean, based on your papers, it's been, what, 10, 15, 17 years or something like that. You kind of pieced all this together based on some papers you've done. Has there, has it, since it's been a long process, has it changed any minds or I mean, what's been the attitude?
I'm beginning to see things that I was writing about 15 years ago. So that seems to be like a 15 or a 20-year delay.
They got to think about it, huh?
Yep. But
Okay.
if you look at, some people don't have the cognitive skills. And it's like there's a dichotomy on complexity. There's one group of people that cannot handle complexity and say we need to develop new tools and techniques to deal with it. And there's another group of people that says, what's the problem? They're dealing with it. You think about cruise companies, airlines, transportation companies, those problems that they have are tremendously complex. And yet everything's there is working. And I'm just thinking about whether the people who can't deal with complexity, or one of the reasons they can't deal with complexity is they're confusing ill-structured problems with complexity. Because there are well-structured problems, ill-structured problems, and what they call wicked problems, which are extremely ill-structured problems. And by definition, ill-structured problems don't have solutions. You have to first convert them to a set of well-structured problems.
Right. Or you develop coping mechanisms until you can break them down and solve them and do things as well.
And then you have to recognize that there isn't a single, except in mathematics, there isn't a single correct solution. There
That's
are
right.
acceptable solutions.
Right. Sometimes you need certain technologies, certain insights that you won't get till years later. And so it kind of hums along. I've seen that as well.
Yeah. You recognize that you can't deal with that undesirability at the time, so you cope with it.
Yep.
But you see that a lot. You see that sometimes in systems design, where you need a capability to do something in a remote location, and you don't have the processing power in the remote location to do it. Or this was happened years ago. So you'd have a telemetry and a command link. But as the technology got better, you could put more and more processing power in the remote location. And so the system split became a lot easier, or the subsystem split became a lot easier. You didn't have that tight coupling of the telemetry link anymore. If I made myself clear on that point.
Yeah.
You need the domain knowledge for that one. Sorry. But like I say to my students, I'm living in Australia. I'd like to go to London for lunch. That's London, England.
Mm-hmm.
And that's lunch today. And that would be, I need to be there in 3 hours. Well, sorry, can't do it. Not with today's technology. Unless I want to get into a rocket and blast myself off. No, I don't want to do that.
Well, we had transporters back in the 1960s with Star Trek, you know.
Yeah, I know, but I've lost it. I can't find it.
Yeah. I guess what I see, Dr. Kasser, is that's maybe the difference between the logical solution, if you want to call it that, and then the implementation solution, where, you know, once you have the logical saying, okay, we need to transport you somewhere, then the second half of that is, okay, when the technology catches up, then you can implement that for you to be able to get on some sort of craft and you know, get there within 3 hours without you having to suit up in a, you know, astronaut suit or something like that. But I guess they are working on some super duper jets now and stuff. But it's, I guess what I'm saying is, I, you know, see people, they don't separate, you know, what are you trying to do with oh, well, we can only solve it one way. We just have this thing and we need a certain speed, like you said, processor. And it's like, well, no, what's the problem you're trying to solve? Yeah, when the technology catches up, then that can be implemented. So that's what I'm thinking is, and I don't know if some people really can separate that because they're always thinking, go straight to the solution without thinking, well, what's your real problem? And
Well,
I think
yeah.
we mentioned that.
That's a really good thing. The Oak Cafe this morning talked about requirements. And so his requirements for the lunch in London, is it lunch in London because he wants to be in London? Or is it lunch because there's a specific restaurant in London he likes? If it's in London physically, then we look at hypersonics and all those things you just mentioned. But if it's a restaurant in London, then if it might not be English food, it might be a really good Indian restaurant there. So is there somebody who has that Indian family recipe, they can produce that for him around the corner or on demand locally? And so there's a whole lot of system thinking approaches to solving his requirement, but you need to understand what his requirement is, define it, and then do the trades.
See, that's the difference between solving the problem or solving what the problem the customer stated or solving the real problem. And the real problem you only get to when you ask Greg's type of question is why. And if the answer is I want to meet my family and friends, well, wait a minute, we can do it with Zoom. Maybe that will work. And talking of Star Trek, do you realize that they never combined the transporter with a replicator for some reason?
That was an X Rev, I guess.
If you think about that, you can replicate something and transport it. And so wherever you are, you can always have something because you tell the remote person to replicate and transport, but they never did it in any of the episodes.
Star Trek, but there's some other science fiction books that did.
I'm not sure that's really useful anyway, because they could actually just transport a replicator and then make whatever they want wherever they put it.
Yeah, but they never did that. At least not in any of the in the episodes or any of the books that I read.
No, I actually been watching the latest series, and I actually saw them do that. They actually they took medicine and put it into somebody's body, like very precisely, and that was replicating, I guess, or transporting. That's a good point, though.
Oh, which?
Yeah, it was the new what's it called? Strange New Worlds is like the second episode. It's very unique what they did.
Biofilters, though.
That's Star Trek.
Right. Yeah. The next, it's the new one, Strange New Worlds. Yeah.
Network shadow, Paul.
Yeah. Don't get me started on my science fiction. I have a whole philosophical issue with transporters to begin with. I think the whole thing is just super creepy. When you start doing a systems thinking approach to it, Yeah.
Actually, reading science fiction is really good training for systems engineering, because you're open to all sorts of possibilities and you learn about all sorts of different domains. And you can go on the internet and you can buy copies of all the classic magazines. You can now get them on a CD and you can go back and read. I'm reading science fiction from the astounding from the 1930s, and it's an interesting perspective of the attitudes of the people and the language. So from 90 years ago, it's different to today.
I actually try to teach my system engineering students that your ConOps is kind of a science fiction novel. You're trying to get some kind of technology that's affecting some situation in the future, and your ConOps needs to express that. So it's a science fiction novel.
Yeah, I used to say the same.
Yeah.
When you're writing requirements for a new system, you're writing science fiction.
Yeah, that's right.
You're writing fiction.
Absolutely. Yeah, technology in the future. Yeah.
But then, Greg, your Oak Cafe might like that I'm giving a talk to the British Computer Society on let's do away with requirements. We can't write them properly anyhow.
Was
What
one
are
of
you
the
gonna
points of
replace
that was
them
one of the
with?
very good discussions. Well, no, but one of the things we talked about was the difference between requirements and specs and standards. I use the approach from the test folks. There's people that treat specs and standards as, and cobbling them all together as requirements. And in a lot of cases, what you do is you try to test, does it do what we need to get done? And if it does, then we do the spec verification validation to find out if the the person who provided an answer was good, or whether or not the people who wrote the requirements and spec standards were just clueless. And so it's either lessons learned to how we do things better in the future, or what we want to tweak for version 2 or the version we actually get beyond prototype for the solution. Going back to Joseph and Bruce's system thinking approach.
Well, it's the comment on, somebody made it earlier, we use application language instead of functional language. So for example, we talk about model-based systems engineering, network-centric, whereas what we should be talking about in terms of network-centric, we should be talking about integrated platforms. And when we're talking model-based systems engineering, maybe we should talk about integrated information rather than models. But then I noticed that the whole focus of model-based systems engineering is to create a set of requirements. And wait a minute, to me that isn't right, but that's another talk, another time, and another place. Or you can look at some of my talks from 20 years ago. It's gone quiet.
Yeah, okay, so
See, I'm on a different wavelength.
yes.
I gave a talk at the University of South Australia that something says, does object-oriented engineering do away with requirements? I forget what the talk was. It was a 20-minute talk and a 45-minute heated discussion.
Well, I always find, Joe, that people spend 90% on the solution requirements and less than 1% on defining that problem, or with, and people confuse, problem requirements like operational requirements or outcomes or needs, with solution requirements. And people say term requirements and people get twisted over axle, think they're talking about each other. And it goes back to the fundamental of this: don't understand the problem. And they don't want to take their resources to understand the problem. They understand a symptom, and they think they want to solve they want to get rid of the symptom. But it's always a challenge in the real world of practicing engineering, is to understand that problem and have people put time and money to understand that problem.
Mm.
That's what I call the original type A systems engineering, that began with figuring out what the problem was. Whereas the modern paradigm is you start with a set of requirements, and those are solution requirements that specify the system that's going to be built. And the whole concept of figuring out the problem, and that the solution requirements are really a solution to the problem, or the requirements for the system are really a solution to the original problem, has been lost. Except in a few who still remember it and do it, and some modern people who do it. But the vast majority, the 80%, don't.
I'm almost to the point of thought of, people into videos and movies. In order to describe a problem, you need to make a movie or a story in a movie about it and describe it that way. And I think that would get a lot of people a handle on those kind of things if they did that.
We did that 20 years ago. There's a paper that we wrote called, I think it's published in Incose, the Operations Concept Harbinger, where we we actually built a model of this or prototype for the Australian Defence Force, where they had a problem in high-level system concept, and so we built them a prototype. It had PowerPoint slides, it had videos in it, and it sort of showed what the system would be like, or a conceptual view of the system, so that they could actually see it. And they really loved it. But there wasn't any further funds for research, so we didn't take it any further. And to me, it was really a dangerous tool, because once the customer saw the concept demonstrated, they focused on that specific way of implementing the solution. Because all that Harbinger was supposed to do was to show, look, we can solve your problem in several ways. This is one of them, but it may not necessarily be the best one.
We used an example this morning about, looking triage, for trauma. If you're looking at the problem and you're on the street side and somebody just got hit by a car, the best way to solve the problem may be do this, do that. You can keep the person alive and everything else, but they may be scarred. They may have some issues and everything else. If they're in a hospital, a primary hospital, you may be able to put some life support there, and you may come up with a different solution that solves the problem, and you can treat them with no scar, no follow-on, everything else. And you look at it's a completely different way to look at the problem, but it's the same problem. It's just different resources, different time constraints, different resources. And when you talk about aviation and so life systems and everything else, there's a lot of cases where you need to get out now, or your system has to address the problem right away, as opposed to optimally. And there's a lot of folks that do the doors solution and spend 20 years optimizing the nouns and the grammar and the font, and they get a great solution. But the question is what have you lost during the 15 years that you could have gotten done while you're optimizing a solution for that last 0.5% of capability?
But Greg, your example, it's with the triage at the accident site and what happens at the hospital, they're not the same problems. The problem at the accident site is to keep the patient alive until they can get to the emergency room. The problem in the emergency room then becomes to deal with the trauma.
Again, I understand that if you're in a city environment, but in some places where you're out in the outskirts, or like the military where you're out there, you're not going to get them back there in a time. So you're basically having to solve the problem, at least an 85% solution, before you do the transport. And so
you have to fix them up. The problem then becomes you have to fix them up so that they can be moved. Or it's an immediate problem. The long-term solution of dealing with a wound and the treatment that sort of brings people back to normal afterwards is not the problem right at the location. You got to
it becomes a two-part problem in one case. In the other case, you may be able to look at both problems at the same time.
You may be able to. So if you know what the overall chain of problems are, you can make decisions. Either time you have to make a decision, if you're looking at it locally, sometimes it doesn't matter what you decide. But if you look at the overall chain, you will realize that if you make one decision, you will block certain activities further down the chain. So you make the decision that allows you more options or more activities further down the chain. So you're right in the sense of you have to know the overall problem chain, but the problem chain, each problem can be different. And if you think about it in our system development problems, the first problem is to create a set of requirements. Once we create a set of requirements, the next problem is to create a design. The next problem is implement design. The next problem is test the design. the next problem is, and so on until we've created a system that works. So the whole process is a chain of problems. Problem solution, problem solution, problem solution.
Yeah, and the example you gave with the bring him home is the family systems, and the fact is what risk can you have during dealing with each of the interfaces between those systems to get the optimum long-term solution for the full picture.
True, and sometimes you don't have the time to do the optimum long-term solution. It's like you're in a situation where if you had certain medication, you don't have to amputate, and you don't have that medication, so you have to amputate. It's you deal with what you have at the moment and make the best decision you can at the time, and that's all you can do. That's decision making. Although
for anybody who has not attended the cafes very often, this last 3 or 4 minutes, it sounds like a cafe.
Yeah, well, this is what we do in the cafes, and sometimes my class does this because we could have this decision where we're talking about problem solving, short-term, long-term solutions, and people could relate to it in the different domains. So somebody could talk about it in the automotive industry. Somebody could talk about it in some other domain. I had a great example in Singapore where they were doing some road works, and what they wanted to do, and they tore up a whole section of the sidewalk. So what they wanted people to do was to walk round that torn up section alongside the sidewalk and then come back to it. Well, what did people do? People stepped out into the road and took the shortcut. So eventually they put up a fence. And so people, if they wanted to walk in the road, they would have to walk in the road from the start of the fence, which was a much longer walk in the road. And that's what they were doing because it was still shorter than taking the detour, which meant they were exposed to traffic danger for longer. So the solution didn't take human nature into account. So it's not, things are not as simple as they seem. I think we run out of time.